Well, I can't tell you how happy I am to be here today. When I boarded the plane this morning at Boston, one of these little commuter jets, they invited passengers who were queasy to step out because there were going to be 20 to 40 mile an hour gusts coming in, which was in fact the case. In fact, there was a moment there where I was sure that the trajectory of the plane was not an unknot. And it's knot theory that I want to talk about today. Certainly a favorite object for mathematicians and physicists is this. Suppose C is a smooth closed curve. And A is a connection or a vector potential. Then parallel transport around C via A is a favorite geometric object and a favorite physical object. Physicists denote this by the path-ordered integral around C of A. Path-ordered because the group of the bundle may not be abelian. So somewhere in here we have a manifold M, which in fact will be M3, and for the purposes of this talk will be R3, and we'll have a principal bundle G, but it will be M3 cross G. And we're talking about connections on that principal bundle, or vector potentials with values in Lie algebra for that principal bundle. An interesting function is the trace. Well, I'm taking arbitrary G. I mean trace relative to some representation of G. If you wish, take G to be in SUN or UN. The trace of parallel transport around the closed curve. And in physics, this is denoted by the Wilson loop functional, depending on C as a function of the vector potential A. After Jones did his remarkable work relating indices of subfactors of rings of operators to knot theory, there were reasons to believe that, in fact, you might be able to get invariance of knots by taking this wonderful function that depended on, like for the knot C, the curve C being a closed curve not intersecting itself now, say a knot in R3 or wherever, and averaging over all A. So the idea is the function depends on A. So on the other hand, let's average over all vector potentials this particular function. And if we average, then it shouldn't depend on A at all. Now the question is, what kind of weighting should we use? We wouldn't expect this thing to be integrable in any sense, so we need here some kind of oscillatory integral which doesn't depend on the metric. Well, in 3 dimensions there's a very nice one, namely the Chern-Simons function of A. And I remind you that Chern-Simons of A is a secondary characteristic class whose differential on the bundle is C2, or the first Pontryagin class, and it's 1 over 4 pi squared. The integral over the 3 manifold, take it to 3 sphere if you're worried about infinity, of the trace in the representation of A wedge dA plus what's called 2/3 A cubed. A is a 1 form. Here's 2 form. Wedge them, take their inner product. That's what the trace does for you in the Lie algebra, or wherever. Here's a 3 form which is A bracket A inner product with A. That does not depend on the metric of the manifold. It does depend on the metric of the Lie algebra or in the representation you're talking about. So strictly speaking, we should talk about the group G and chi, but I will submerge that dependence. Now, we have something here which is independent of the metric. On the other hand, it should be invariant under automorphisms of the principal bundle, gauge transformations. We know that if you perform an automorphism of this bundle, that this Chern-Simons term will change by a multiple, by an integer, multiple of 2 pi, I should say. And therefore, if we want this to make sense as an invariant function under gauge transformation, we better assume that this coupling constant lambda is an integer. So now we have something, this integral is some interesting function. It's called the expectation value of the knot C. And it really depends on K, and it depends on the group we're talking about, if it makes sense. So, sort of in a natural way, I've tried to say, God, if we could integrate, if we could make sense out of this integration, then we would have an interesting invariant of the knot C. There's one other factor here. I really want, quote, the total measure to be 1, so I ought to divide out by what's called a partition function. To normalize everything. And now the issue is how to make sense of this integral. Well, it was Witten's great insight to say, I'm not going to worry about directly what this path integral means, but I can relate it to a conformal field theory, and through the conformal field theory and the formal properties that path integrals are supposed to obey when you have a manifold with boundaries, their expectation values, state space. There's a whole intuition of path integrals that come from physics, which tells you how this function is supposed to behave. And in that way, he really was able to give almost an axiomatic treatment for what this functional of C is, and it then ties in with the Jones polynomial in a way that is pretty well understood now from a combinatorial point of view anyway, Reshetikhin, Turayev, for example. There are other approaches as well, very functorial category type approach also. Others of us, Dror Bar Natan started this, and then Scott Axelrod and I did this for arbitrary manifolds. He did one piece of the R3 case. Decided that we do know one aspect in which this integral makes sense, and that's the perturbative aspect. So we do know what it means for the perturbative aspect, for the perturbative series, what this is. And we would like to see whether you really do get knot invariance if you take a perturbative expansion in the traditional way. For physicists, I'll say it turns out that perturbative expansion is very simple, can be expressed in a beautiful way in terms of differential forms. There are no counter terms. The theory is renormalizable. There are no counter terms. There are no overlapping divergences. Everything converges in this theory, and so it turns out to be a theory which one could explain as a mathematical theory without any reference to physics whatsoever. Now, what do I mean by that perturbative expansion? What I mean is I want an expansion in 1 over k in the following way. I have a k in front of here. what I'm going to do is put a square root of k here, a square root of k here. Now I have the square root of k cubed, so I better put a square root of k down here. And now I want to change variables and call my new variables square root of k. So I better divide out square root of k here. I better divide out by the Jacobian change from the square root of k over k. That will be a 1 over square root of k to the dimension of this big space A, but I also have it down here, 1 over the square root of k to the dimension of the space. And by rights, that's the reason for normalizing. Whatever that means, and we can say what dimension means in this infinite case, these two are going to cancel each other. And now what happens in this expansion is I've replaced k here by this term, which I'll get rid of the k's here, and I just have a square root of k in the cubic part only. So what the exponential looks like is an e to the I and the first part is, I'm going to write it in more operator language. A wedge dA inner product is the same as A star of dA plus a cubic term, which is 2 over the square root of 3 times k, and here I have an a cubed term. And I will get to the fact that what one starts to mean, and of course down here I have the same thing. I'll just call this in the denominator. What starts the perturbative theory is you're going to really treat all this formally and see what happens in the expansion in terms of 1 over the square root of k. Well, physicists know automatically what to do, but it's largely a mathematical audience, so I thought I'd warm up by taking the abelian case. So let's see what happens in the abelian case. It's very instructive to see what this looks like for the abelian theory. Remember, this has an a bracket a in here. It isn't there at all. So now what I'm doing is trying to integrate. Now let's rewrite it. I'm going to erase this. I'm going to rewrite it. We're just talking about the case where the group, say, is a circle. We're talking about ordinary forms. And I want to rewrite it. The expectation value of C in the abelian case is, in the numerator, the integral of dA over A, e to the I, and here I have A star dA, e to the I. Now we have an honest integral around the curve C. And in the denominator, I just have this without that piece in it. Okay? You should recognize that this is the curl operator. We're talking about one forms in 3 space. And really, in the exponent, what I have is A, well, I can put it on the other side. I have curl A plus, and I can think of this integrating around C as a linear functional on A. I'm going to write it as C inner product A. It's a current, literally a current, applied to one forms A. Well, now I'm going to complete the square. I'm going to write this as equal to curl of A plus curl inverse of C times A plus curl inverse of C. And you'll see if I do that, I get this term. I should have had a half over everything. Whenever you have a quadratic, you should put a half on the whole thing. So I really want to deal with a half here, put a half here, and then I'm have to subtract off the last term, which is this times this, or C curl inverse of C. That's what it looks like. Now, of course, you should object immediately. Curl inverse doesn't exist because you've got lots of exact one forms which are killed by the curl operator. So curl inverse doesn't exist. On the other hand, we're looking at the dual space. C is a closed curve. It kills all the exact differentials. So it's okay. These are functions on one form's modulo the exact, so curl inverse really makes sense on C. So now you see, I substitute here this into the integral. What will I get? Well, this part doesn't depend on A at all, so I'll get e to the minus I over 2 C curl inverse C. And then what I get is just this piece, but A replaced by A plus curl inverse C. I use, someone earlier, one of my former students here, accused me of becoming a physicist and not a mathematician at all, and you're about to see that in operation. I'm going to say the d of A plus curl inverse of C is d of A. The dA is supposed to be Lebesgue measure. It's translation invariant, even though it doesn't make sense. But, you know, if we really wanted to get technical about it, we're talking about a Gaussian, really. And Gaussian measures on Hilbert space do exist, and you can check that what I'm doing is really correct if you put enough machinery into what I want. But I make this change, so I'm really calling this A tilde if you want. Make the substitution, and you'll see that what I had left, this term and this term cancel, and so here's the answer. So we can integrate, providing we now can make sense of this. So purely formally, in the abelian case, we end up with this as the answer if I can make sense out of this expression. Now let's see what the problem with that expression is. I guess you can see over here. We need to know what curl inverse is as an operator and what curl inverse C inner product C is. Well, curl inverse is an integral operator with kernel as a function of two variables. It looks like this. And this is a function on R3 cross R3, and as usual we would expect it's an order -1 operator. We expect a singularity along the diagonal, so you've got to avoid the diagonal. And then what it looks like is x minus y over the norm of x minus y cubed, r vector r over r cubed, dx vector wedge dy vector. All of these are vectors. So it's the determinant of those rows, which is a two-form here. How do I apply it to a form? Really, curl was defined on one form. How do I apply it to a form? A one form. I take star the one form, that's a two form. In the y, wedge it, that gives you a three form in y. Integrate, and I end up with a one form in x. And that's the transformation I'm talking about. And what happens here is that C curl inverse C is equal to the integral over C of, say, C of S minus C of T over C of S minus C of T cubed dc ds wedge dc dt. This integral over S and T. Okay? That's what happens when you unwind what curl means. And now we stare at it, and we see that there's a difficulty. When s equal t, this blows up. So I worked very hard to get this far, but now I have to do something and try and understand what this integral means when s equals t. Well, let's test this by seeing what happens when we took two different curves. Suppose we took two curves that didn't intersect and see whether the integral makes sense now. We would expect this integral to make sense because C1 and C2 are now currents or distributions which are disjoint. So we would expect this to be reasonable. And if you check, you see what this equals is the double integral of C of, say, C1 S1 minus C2 S2, I'm changing variables, C1 S1 minus C2 S2 cubed, dC1 ds1 dC2 ds2 ds1 ds2. Now you should recognize this formula. And the hint is the title of my talk. If I put 1 over 4 pi here, which I should have carried along, this is the linking number, I'll call it L, of C1 and C2. Meaning that I've got two curves. I take the map that sends S1 of S2 into C of S1, C1 S1 minus C2 S2 over their absolute value. This is a map of S1 cross S1 into a unit vector into S2, and I take, say, the generator of the second cohomology here and pull it back via this map. Or, if I think of it more geometrically, I take the volume element and pull it back and integrate it over S1 and S2. And that's what this formula is. It's the volume element pulled back. I always thought that this is Gauss's formula. I always thought that Gauss's formula he discovered from surface theory, his development of surface theory, but that turns out not to be the case. He gets it out of electrodynamics, his paper on electrodynamics, Ampere's law. Maxwell wasn't around yet, but he in fact gets it from this curl inverse operator, and in fact I'm pretty close to a derivation of this formula from the point of view of electrodynamics, which I find interesting. Moreover, if you think about the electrodynamics, you get the various formulas. You'll see why I want to do this later on. But if you have two curves, and they link, one way of defining the linking number is spanning one of the curves by a disk, which intersects the first curve transversely and counting these are oriented curves, and counting the number of intersections with the proper sign. Another way is taking the curve and moving it out and counting every time it hits, clicks. Electrodynamics tells you to do that too. And pulling it out and counting the number of times before they're completely separated. So either way will give you a way of counting and telling you that you're getting the linking number of the two curves. And now I can explain the title of my talk. That is, here is a formula for the linking number of two curves, which I've put into the context. I'll get back to the case where C1 is equal to C2. But I got in the context of abelian or one forms of this path integral. It was in the attempt of interpreting this path integral that I arrived at this formula for the linking number. And the moment I put in the cubic term and a non-abelian one, then what will happen, if I get that far, is we will get very complicated, more complicated formulas for higher linking of curves. That's what the perturbation theory is going to tell us eventually. Well, let me get very quickly to what happens when you let C1 equal to C2. What you have to do, if they're the same curve, is if you take this curve, you have to pick a framing, or let's say take the normal to the curve. Here's my original curve C. Move it out via this normal. Let's call this C sub epsilon. And then we can talk about the linking of C with C epsilon. And then what you do is you look at the map of C cross 0 epsilon times C epsilon into minus the diagonal at epsilon equals 0 into the two-sphere. In other words, you look at the mapping of the two-sphere for every C epsilon and let epsilon go to 0. This is called point splitting in physics. And as you approach the bad place, namely epsilon equals 0, you replace the diagonal in C cross C by the unit normal. And in that way, you're able to you'll take the differential of this, which will be 0. You'll be able to use Stokes' theorem, and you'll be able to apply Stokes' theorem sort of by replacing the diagonal in C cross C by the normal direction to this curve. This depends on which normal you pick to move the curve away, and so strictly speaking, you have to have a framing of the manifold before you can do this operation. That's lesson number 1. We need a framing. Lesson number 2 is we really have to replace diagonals by a kind of unit normal sphere to the diagonal, and that's where things will take place that'll take care of the blowing up that occurs in this case. So what happens when we do that is it turns out that this turns out to be the linking number of C and C epsilon, which is independent of epsilon but depends on the framing, plus or minus 1 over 2 pi, the integral of the torsion of the curve along C. So the next lesson here is that in fact this integral, although it seems not to depend on the metric, does depend on the metric. The reason is because whatever this measure is, it's sort of Lebesgue measure. It really does depend on metrics. We don't get an answer independent of the metric. A framing is okay. We'll pick a framing that'll only differ by an integer. And the torsion of the curve enters in a serious way. It is dependent on the metric. Okay, I've now made the several points I wanted to make about what happens in the abelian case. The third point I want to make is this business of killing the numerator and denominator. When I made that shift, strictly speaking, z like this is really infinite, and although, so to speak, it's the same infinity, canceling it is a little bit dicey. It's all due to the fact that there's so many, the kernel of this operator is so large, all the exact forms. Physicists have a technology for dealing with this, gauge fixing, ghosts, and ghost determinants. In this case, it turns out to be very beautiful what you do in mathematics, and it's so very natural, I should say. What we really have is one forms into two forms, D, and then we take the star to bring it back for curl. But that's really the basic operator, as we wrote A wedge dA. And we know this isn't a very good elliptic system, but we know how to complete this system. What we do is put in here So we have the natural de Rham complex, which is an elliptic complex, and that is a reflection of the gauge fixing that you do in physics. You can just deal with this complex. And then you have the inverse operators. When we talk about the inverse, we know the curl doesn't have a full inverse. What we do is take the adjoint operator at any place and divide by the Laplacian. And that's as good an inverse as you can possibly get. And it's the integral kernels for these operators, there are three of them here, that play the role of the inverse of curl and takes care of the Gauss terms. And what that comes down to in 3 space is we need, you see, 3 operators, so there are going to be 3 different kernels, and they fit together in this way. Instead of just taking dx dy, what you do is take dx minus y, wedge dx minus y. There are really 3 kernels here. If you split them up, it's best to keep them together. And this is a splitting of the splitting is the degree in the product space. You see, this has a form of degree 2, 0, that is degree 2 in x, 0 in y. 1, 1, that's the friend we started with. And 0, 2, and that's the case of only the y's. And these are the inverses. The 1, 1 we've just described. Here's the 0, 2, and here is the 2, 0 form that you're dealing with, and you put them all together. Now the fact of the matter is, and this is an aside for the present, but I do want to tell you what the general theory here is for the moment. If you want to deal with an arbitrary manifold, compact manifold, and you take a perturbation around an arbitrary flat connection, then you replace these. Here are the connection 1 forms with values in the Lie algebra, and you replace D by the covariant differential, and you do the same thing. And then this gets replaced by the inverse, the propagator's the inverse, which is d star over the corresponding Laplacian. In this way, what you end up with is a 2 form. You end up with an element in wedge 2 of m cross m minus the diagonal cross G. This summarizes the basic propagator and the propagator ghosts. And in fact, the whole perturbation theory can be described completely by this object, which has a purely geometric analytic definition. Everything in the perturbation theory can be expressed by the element L as a 2 form. And its singularities, and the reason I emphasize the Euclidean case, its singularities along the diagonal, near the diagonal, look like this, so that you can, in fact, analyze what happens as you approach the diagonal, and therefore you have a very good hold on the multiple integrals that occur in the theory. Okay, so that's the third lesson, that you really have to gauge fix, which is replaced by what I've just described. That's going to take care of this fictitious, or suspicious, I should say, cancellation of the denominator.
But that Gauss action still, in the numerator, has a kappa in it, and in the denominator not. So they don't cancel.
Oh, you mean the determinant of the square root of k. I'll come to that in a minute, okay? That takes care of itself with the 0 modes. All right, so yes, a couple more comments about this case. We see I don't want to spend too much time on it, but I do want to give you one application of the case of C1 and C2. You see that if we had put in a C1 term here and a C2 term here, we would have gotten curl inverse C1 plus C2, inner product C1 plus C2 as the answer. And then the mixed terms will have the winding number in it, and that's occurring in the exponent. So if you had two such things, you'd end up with a term in the exponent, which, if I use my right scales, which would be e to the I pi of the linking number, I should say, of C1 and C2. Now that turns out to be of some interest in condensed matter physics, what's called Anion Theory. And the idea is it's what's called transmutation. If you took two particles and you did this, and then you went on, and then did this so that they linked this way as you went off to infinity, and you have laws of electromagnetism, and now you turn down this Chern-Simons term, if they're linked by 1, you just get this factor, which would be a minus sign. So that means normally bosons, if you interchange, it has no effect, but this would mean they would change from a boson to a fermion, and vice versa, by this device of putting in an abelian Chern-Simons, if you want, in the theory. I'm told that you get somewhere with the quantum Hall effect this way, but I haven't read those papers. I think some of that work was done here a couple of years ago in the condensed matter group. So it already, for some people in high temperature superconductivity, this set of ideas is useful. But now I want to go on to the non-abelian case, and I want to say what I mean by the quantization of Gauss's formula for the linking number. Notice that the way I did it, this occurred, let me write it out. What I'm integrating is e to the I integral of C1, e to the I integral of C2 in this integral, but the way I've set things up, all I see is the plus or minus sign, because I ended up with a term which was e to the actually minus I pi of the linking number of C1 and C2. I don't actually see the linking number, just the parity of it. If I want to see the linking number, I have to take a power series. So I've got a certain integral here, dA, e to the I, the quadratic term, a curl a, like this. When I want to see the linking number, then I really want to expand this term in a power series. And what I get is 1 plus I integral of C1 of A, 1 plus I integral of C2 of A. When I multiply, take these outside, I get an integral C1, integral of C2. Then I have this big path integral. And here, and two i's make a minus sign, I'm going to get a term which is A at a point on one curve times A at a point of the second curve. The linear terms will not be there because this is even, and this times with that would be odd. If I change A to minus A, I change the sign of the integral. So here's the first non-trivial term, and now I've got to take a few minutes off and say a word or two about perturbation theory, but anybody who has played with it knows that this is going to give me the Green's two-point function or the two-point function for the inverse, and this way I recapture the integral formula for the Gauss linking number. So here we really do see the Gauss linking number, and this is what I want to get by, I want to soup that up using the full form of Chern-Simons, not just the abelian case. But now I have to say a word about perturbation theory because most of you don't know it. I'll be brief. And it's just a matter of knowing a lot about Gaussian integrals. So the first thing I remind you okay. Next, if I'm on a vector space, to the dimension of this space, this will be just T self-adjoint positive definite. Diagonalize, you have separate integrals. You'll get 1 over the square root of lambda for every eigenvalue. This is 1 over the determinant of T to the 1/2 power. You actually want an I in here in our cases, so you're going to take these formulas and analytically continue to the complex plane. That also allows you to take care of minus signs. So we find out that the integral of e to the I tvv, where t is now just self-adjoint, dv over the square root of 2 pi to the right order is equal to 1 over the determinant of the absolute value of t to the 1/2 power. And here, e to the I pi over 4 times the signature of t, if you take into account the sign, plus and minuses. If you left the I out, then you'll end up with the signature minus the dimensions, if I recall.
What are the limits of integration now?
Over the entire space. This is over R. This is over V, this finite dimensional vector space. This is over the entire vector space. Now, I want to use, I'm going to do one more point. Well, let me write the next one down. Of course, that reminds me of my 2. Otherwise, the square root of 2 pi is wrong. Now I'm going to take a set of linear functions. Let's take 2 of them first. Okay? L1 and L2 are linear functions, dv over this. If t is non-singular, then what you'll end up with is 1 over the rest of this stuff. That is determinant, signature. And the other you'll get is T inverse of L1 inner product L2 for 2 points. And that's what I meant over here. You've got a quadratic and you've got linear functionals. It's true that they're delta functions. And then you take the inverse, you'll get the Green's function for it integrated over C1 and C2.
But the Green's function didn't exist because for the other case you had the curve, just the closed, and then these exercises cancel. But here you don't have that.
Well, you're integrating over C1 and C2. Well, and so if I divide by the fundamental measure, then of course I'll cancel determinant and signature. Now we want the generalization of it. If I put many of them in here, the odd number will vanish because of the change of v to minus v, say L of 2R of v. Then what happens is you get a product of T inverse Li of Lj summed over all the possible combinations of putting I and j together. Several comments before I use it. Notice I need to have the inverse. That was this problem of writing curl inverse, and that it's on the right space. That's the problem of gauge fixing that I described more mathematically over here, and it just takes care of itself. So you really have an honest propagator, meaning you really have an inverse in these things, in the infinite dimensional case. And the other thing I want to say about the infinite dimensional case is that signature and determinant, we know what they mean. There are ways of regulating the determinant. The signature is the eta invariant for this operator. And we also know what dimension means. Dimension is the value of the zeta function at the origin, because the zeta function of an operator, zeta function means the summation of lambda j to the minus s. And so if you put s equals 0, and the zeta function is not a pole at s, doesn't have a pole at s equals 0, this plays the role, the value of the zeta function at the origin plays the role of dimension in these infinite dimensional models. So it turns out you can say what dimension means, what signature means, what determinant means, and so these terms, which actually do appear in the theory, when you say compute the partition function, they are what the regularized meaning from elliptic analysis tells you. So your question about 1 over the square root of k, because there are zero eigenmodes, what happens is you get 1 over the square root of k to the Euler characteristic of this elliptic complex. It's what actually appears. All right, I'm now ready to write the expansion out, at least for the first term, and I'm almost finished. So I'm just going to use this in terms of a power series. Let's write down what I first did. Oh, I shouldn't. I'm glad I didn't quite erase this. Feynman drew pictures for the pieces in this product, and they are very succinct and very useful. So, for example, suppose that we wanted to integrate. I do have to do one little bit more of analysis. Suppose we did have e to the I tv v over 2, but now I put something else in the exponent, which was some polynomial in v. For example, if we picked a basis, suppose I took summation of vi cubed with some scale in here. In our case, 1 over the square root of k. Okay? Now that's very hard to compute. Makes sense. Well, oscillatory will make sense. If t were positive definite, with minus it would make sense. But certainly, as a perturbation theory, it will make sense. I'm going to have a 1 plus 1 over the square root of k summation of vi cubed plus, and I should need the next term, plus 1 over k 2 factorial summation of vi cubed squared. Okay? Now again, this is odd when I try and integrate, so there won't be a term like that. This one is like our old integral. So the first term that enters is this. And I want to write vi as the linear function, which is Li, the dual basis, applied to v. So what I'm getting here in terms of this product is I'm getting the summation of Li of v cubed squared. So a typical term in here will be an Li of v cubed times an Lj of v cubed, and then some summation out here. And what does this rule tell you? It says I combine these and take T inverse. So Feynman says, well, here's I and j. Every time I draw a line between them, that means I take T inverse of the first Li inner product with the second one. So I could take LILJ coupled, LILJ, LILJ. That'll give me 3 of these. Or I could take Li, Li, Lj, Lj. It leaves an ion in J. That'll couple Li and Lj. So here are the two diagrams that go with this cubic squared, so to speak. And then I would sum over I and j. This tells you take the propagator between them. This is called a dumbbell diagram. This is called a sunrise diagram. I'm about to use them in the context that we're in. But you can go on. You can see that if you have further powers, you'll have more points, and then you'll have a sum of diagrams which explains how you put them together. Okay, now let's go back to what my integral was. And let's see, we started about 5 minutes, or 10 minutes late almost. Give me another 5 minutes or so. What did I have? I had an e to the I, a star dA. And then I had an e, what we called the Wilson loop, the cubic term, which is e to the, well, we had the Wilson loop I'm writing this way. And then we had the cubic from here, which was e to the I, 1 over the square root of k, of, I'll call it the trace of a cubed. We know what that means. You take a1 bracket a2 dot a3, what that means. It's called the interaction term here. And now we expand all this in power series. Remember, this had a square root of k2 because I changed a to square root of k. We leave this part alone, and now I'm going to have I don't have time to explain that even in the non-commutative case, that's why it's called path ordered, that you can actually write this out formally as a series. Because I'll tell you how to do it. Remember what parallel transport means. It's not an integral anymore, it's a solution to a differential equation. Namely, u dot is, u inverse u dot is a. To solve that differential equation, you can solve it formally by integrating more and more times, by repeated integrals. That's what you do here. There's a trace in front of here. I'm going to put all traces, this trace outside. So you'll get 1 plus, the first term is the integral from 0 to 1, say, if that's what we have, a. Then with a 1 over the square root of k. Then we'll have a 1 over k, the integral, double integral. Here we'll have, say, a of s1 ds1 from 0 to s, and a of s from 0 to 1, and so on down the line. That's this term over here. Then we go on. Let's take the second term. We'll have 1 plus I over the square root of k with a 2/3, and a cubed. I'll call that a cubed at some point u in the space. Then we'll have the square of it, 1 plus 1 minus 4i over 9, a cubed at u, a cubed at v. And this will have integrals attached to it. We're going to integrate over u, we're going to integrate over v, because that's what this cubic means. You take, in the Chern-Simons, you integrate over the manifold. So in these variables, you're integrating over u and v. In these variables, when you bring them out, you're integrating over the curve that you're talking about. All right? So we write all this out, and now we have the rule. We say, take the propagator, meaning the extended propagator we talked about, and couple these things together, and you're going to get multiple integral formulas that are generalizations of Gauss's formula. So rather than write them out, I'll draw the pictures. For a single curve, just not the linking number, but just for a single curve, you get a picture that looks like this. Here's my curve C. Here's my U. There are 4 points. Every time I take one, I have a square root of k. This is going to be the first term in the expansion, a 1 over k squared term. And that diagram corresponds to a multiple integral. What that multiple integral is this one. It's L of U S1. L is the basic propagator. L of U S2. L of U S3. Right? And the du integral is over the 3-manifold R3. And the other integrals, 0 to S1. So say S1 is 0 to S1, 0 to S2, 0 to S3. So there is an example of a generalization of the self-link. The big thing is that even though the L's have singularities, you end up with something which is integrable, well-defined, and in fact, if you put the diagrams together, we'll add them up as with the usual weights, you end up with something which is independent of the metric and independent of perturbing the curve. You do get an invariant of the manifold. So the other piece of this one is, I'm going to draw a couple diagrams and then I'll come to some conclusions. The other piece is where you don't have any U, you'll have, again, 4 points. And you've got to connect each one to every other one. I've now indicated the diagram, and you put the propagators in the right place, as indicated. Here's an example where I really started by saying I wanted to give you a generalization of the Gauss linking. So let's take 2 curves. Then here's what you would get for 2 curves. The first non-trivial case. You'll have UV lying in the ambient space. You integrate over those. And you have S1, T1, S2, T2, and here is the propagators. Between them, plus or minus a term where you don't integrate over the ambient space, like that. Okay, now I should, I think, give some references. I did start by saying that Droba-Natan did the first term in the perturbative expansion in his original paper. I've mentioned Witten. I mentioned Scott, Axelrod, and myself. We actually did the partition function and got manifold invariance that way. Axelrod has gone on and done the theory with curves in it, with curves and links. I should mention Kontsevich, who independently found the basic 2 form, not quite this way. We did it sort of by Hodge theory. He did it by the appropriate de Rham theory. Then there's Vasilyev. And then there are various people who put Vasilyev together with the perturbative theory. Certainly Joan Berman, and also Jorma Barnaton. And I see I've left, there was joint work with Joan Berman and somebody whom I've left out. I'm sorry, I've left this name out. So the state of the art is that one understands much of these knot invariants from the combinatorial point of view. This would be the analog of saying that we're going to define the linking number by counting the intersection with a surface that one of the curved bounds, or by pulling apart and seeing what happens under intersections. At least for me, I'm just beginning to understand the relationship between the integrals and the combinatorial approach. I think that needs to be understood a lot better than one understands now. So, for example, for this curve, I know that, for this set of integrals, I know that it's invariant under isotopy. I know that it's zero if you haven't got a link. I don't know, I'd hope it isn't zero on this example. The old Whitehead example of two curves that are not linked, but you can't pull them apart anyway. I don't know whether this separates that or not, and I don't know the relationship, say, for example, between these integral formulas and Milner's old mu invariance for links, although there seems to be some understanding of the relationship between the Vasilyev invariance directly and Milner's old work on links. Okay, I have one more comment to make. This is something that I've been focusing on with Scott Axelrod for some time now, but really it only illustrates something that's been happening in the interface of geometry and quantum field theory. And that is, what's happening is that many classical invariants of geometry and topology can be quantized. Mostly, all that happens is there's a quantization at the semi-classical level, and that's all there is to the theory. It ends there. This is the only geometric example I know where a semi-classical theory is not very interesting, at least not to me, and you get something new when you go beyond it. But the comment I want to make is, systematically, we see quantum field theory in these geometric situations quantizing known invariants we have and leading to some new invariants. Thank you very much.
When you talked about the endpoint expectation values, you emphasized that the coupling constant should be an integer in order for everything to be gauge invariant. What effect does that have? Does that have any pathological side effects when you start doing the perturbation expansion in 1 over square root of k? You don't see anything strange?
No.
So you think that in fact it should be well defined for non-integer values of k, or?
I don't care. It's just the terms of the expansion. I'm interested in. So let me put it this way. See, I didn't erase the quantum field theory here. I could have written, if I wanted to, I could have written, let me go back, think about analytic torsion, which was a reflection analytically of Reidemeister torsion. Ray and I were motivated in trying to find an analytic expression, but if you look, you find that you can check directly that if you take the variation with respect to metric, it's independent of the metric, so you have an invariant. So you could have asked, what invariant is it? If you didn't know what it is you were trying to do. In the same way, here, I could simply have written down the multiple integrals. Complicated, but I could have said, let's check whether they depended. You see, the propagator depended on a choice of metric, the way I did it. I could have checked to see what happens as you vary the metric. It turns out there is an anomaly, which we know. If you subtract that off, you get something independent of the metric. And I could have said, here's some new invariants. You see, and these are each term in the asymptotic expansion. Oh, I don't care whether the k's were integers or not. It's just the powers that count. So on the one hand, you get invariance this way. On the other hand, since it's known, at least for special cases of manifolds, what the closed form of the partition function is, as a function of k, you would then want to check whether, if you expanded that in 1 over k, the known total solutions, like the three-sphere, whether you are getting the terms in the expansion, the numbers that we're getting by these multiple integrals. For the three-sphere, the answer is yes, but it's non-trivial that the answer is yes. It's still open whether it's true for all three manifolds. Yeah, I think so.
How do you relate theory with the combinatorial theory?
Well, that's a very long story, you see. That's why I listed these people and Reshetikhin and Turayev. There's enormous literature here, which I myself actually haven't absorbed. I've been concentrating on the analytic and integral formulas rather than the combinatorial ones. But these people have done a considerable amount of interesting work on the subject.
Well, let's thank our speaker again.
Thank you.